The comet arrives in silence. It has been traveling for tens of millions of years, perhaps hundreds of millions, through the cold between stars where temperatures hover just a few degrees above absolute zero. No one knows precisely when it began its journey, or from which stellar nursery it was cast out into the darkness. What is known is this. On December 29, 2024, astronomers using the Asteroid Terrestrial Impact Last Alert System, ATLAS, a network of telescopes in Hawaii and South Africa, detect something moving against the fixed stars. The object carries a designation that sounds more like a coordinate than a name. CT 2024G3, later refined to 3I/8LAS when its trajectory confirms what the mathematics already whisper. This is the third interstellar object ever identified, after 1I/Oumuamua and 2I/Borisov, and the second interstellar comet. It moves with the velocity of exile, roughly 26 kilometers per second relative to the Sun, fast enough that no elliptical orbit can contain it. The shape of its path is hyperbolic, open-ended, a curve that enters and exits without closing. Gravity bends its trajectory as it falls sunward, but cannot capture it. In this way, it resembles a stone skipping once across the surface of our star's influence before returning to the deep. The comet measures perhaps a kilometer across its nucleus, though exact dimensions remain uncertain. This is small by cometry standards, modest, unremarkable in size if not in origin. Its surface, never observed directly, is presumed dark, covered in a crust of organic tars and silicates left behind by countless sublimations in some previous stellar system. Beneath this crust, ice waits. Not water ice alone. Though water is present, carbon monoxide ice dominates, along with carbon dioxide, methane, molecular nitrogen, volatiles that freeze only at the extreme cold of the outer regions where planets form, or fail to form, or are ejected before formation completes. The comet carries within its frozen heart the chemical signature of its birthplace. Spectroscopic analysis will later reveal ratios of isotopes, abundances of molecules, structures that speak to formation temperatures and pressures entirely unlike those in our own Sun's protoplanetary disk. It is, in the most literal sense, alien, not in biology but in origin, a fragment of matter assembled under a different star's light, probably a star that still burns somewhere in the Milky Way's sprawl, unidentified, unaware that it once shed this small piece of itself into the dark. By early January 2025, the comet brightens. It is still beyond the orbit of Mars, but sunlight begins its slow work. Photons strike the dark crust, and energy accumulates. The surface warms from the ambient cold of space, perhaps 100 Kelvin, perhaps less, to temperatures where the most volatile ices begin their transformation. Not melting, for pressure is nearly absent here in the vacuum. Sublimation. The direct passage from solid to gas. Molecules breaking free of crystalline matrices and streaming outward into emptiness. The first jets are detected not as visible phenomena, but as changes in brightness and spectral signature. The comet develops a coma, a cloud of gas and dust that scatters sunlight, making the nucleus appear larger and more diffuse than it truly is. This coma does not form evenly. Observations show asymmetry from the beginning, one hemisphere brighter than the other, suggestive of active regions concentrated on one side of the nucleus. This is common enough among comets. What is less common, what will become the central mystery as observations accumulate, is the temporal pattern of these emissions. Most comets, when they begin to outgas, follow a rhythm tied to rotation. The nucleus spins, carrying active vents into sunlight and then into shadow, producing jets that pulse with the regularity of a lighthouse beam. Rotation periods for comets typically range from hours to days, and the resulting light curves, graphs of brightness versus time, show clear periodicities. Peaks repeat, Valleys repeat. The mathematics of Fourier analysis can extract these frequencies with confidence, revealing not only the rotation rate but often the geometry of the active regions themselves. 3I/Atlas does not cooperate with this expectation. Initial attempts to measure its rotation period yield ambiguous results. Some analyses suggest a period near 10 hours, others find different values, or multiple overlapping periods, or no strong periodicity at all. The light curve shows variability, certainly, brightness increases and decreases over time scales of hours, but the pattern refuses to stabilize into clean repetition. Each peak differs slightly from the last in amplitude, in duration, in shape. It is as if the comet breathes irregularly, each exhalation following its own timing, unconnected to the mechanical regularity of spin. This irregularity is noted but not yet understood. Astronomers continue their observations, accumulating data points, building up the record of 3I/Atlas's passage through the inner solar system. The comet reaches perihelion, closest approach to the Sun, on January 13, 2025, passing within approximately 13 million kilometers of our star's surface. This is close, closer than Mercury's orbit, close enough that solar radiation intensity increases by a factor of hundreds compared to the comet's earlier distance. Surface temperatures climb, sublimation accelerates, the coma brightens dramatically, becoming visible to the naked eye for observers in the southern hemisphere, a faint smudge in the dawn sky. And the jetting intensifies, but still without pattern. Ground-based telescopes and space-based observatories turn their attention to this visitor, capturing spectra, measuring gas production rates, tracking the evolution of the coma's structure. Carbon monoxide emission lines dominate the spectra, far more than would be expected from a solar system comet at this distance. Water is present but secondary. This confirms what the trajectory already suggested. 3I/Atlas formed in a colder environment than the comets native to our Sun, a place where carbon monoxide could condense and remain stable over billions of years. The mystery of the irregular jetting becomes more pronounced as data quality improves. High-cadence photometry, brightness measurements taken every few minutes, shows that outbursts do not correlate simply with rotational phase. A jet might activate, increase the coma's brightness by a factor of 2 or 3, then fade over the course of an hour. Several hours later, another outburst might occur, different in intensity, different in duration. Sometimes two outbursts overlap. Sometimes long periods of relative quiescence stretch between events, during which the coma dims and the comet appears almost dormant before the next release begins. Planetary scientists propose various explanations, each plausible, none yet confirmed. Perhaps the nucleus is in a tumbling rotation state rather than spinning around a single stable axis, which would complicate the pattern of solar heating. Perhaps the active vents are not fixed features, but transient, opening and closing as subsurface ice sublimates and the crust fractures and reseals. Perhaps thermal lag plays a role, heat taking time to penetrate inward through insulating layers, so that jets activate hours after the surface above them has rotated into sunlight. Or perhaps the interior structure is deeply heterogeneous. Pockets of different ices distributed unevenly, each responding to heat on its own schedule. The comet does not answer these questions. It only continues its outward climb, moving away from the Sun after perihelion, following the hyperbolic arc that will carry it back into interstellar space. The jetting will fade as solar heating diminishes. The coma will dissipate within months. 3I/Atlas will become too faint for all but the largest telescopes to track. Within a year or two, it will pass beyond the orbit of Neptune, returning to the cold that shaped it, carrying its irregular rhythm back into the dark from which it came. Only the data will remain: brightness curves, spectra, images. evidence of a visitor whose heartbeat never quite matched the expectations of those who watched it pass. The first asymmetric breath begins not with drama, but with a slow accumulation of energy beneath a dark and ancient crust. Sunlight falls upon the surface of 3I/Atlas in early January, and the physics of heat transfer begin their patient work. Photons strike dust grains, organic molecules, tiny fragments of silicate embedded in the outermost layer. Energy converts to molecular motion, vibration, rotation, the microscopic dance that manifests as temperature. The surface warms from perhaps 90 Kelvin to 100, then 120, climbing degree by degree as the comet falls closer to the sun. Beneath this warming surface, ice waits in darkness. The crust itself is porous, riddled with voids and channels left by previous sublimation events that occurred perhaps billions of years ago, perhaps in the comet's original stellar system before ejection. These voids act as insulation, slowing the penetration of heat but not preventing it entirely. Thermal conduction proceeds, molecule by molecule, lattice by lattice, carrying warmth downward into layers that have not seen direct sunlight since their formation. The process is slow. Minutes pass, then hours, as heat diffuses through the first millimeters of material, at some depth, centimeters below the surface. Perhaps deeper, carbon monoxide ice begins to stir. The temperature at which carbon monoxide sublimates depends on local pressure, but in the near vacuum conditions within the comet's pores, the threshold lies near 70 Kelvin. The subsurface layers, warmed by conducted heat from above, cross this threshold not all at once but gradually, in patches. Wherever the geometry of pores and the distribution of sunlight and the composition of overlying material happen to align, individual molecules break free from the ice matrix, becoming gas, expanding into the void spaces around them. Pressure builds, gas molecules collide with pore walls, with each other, with the remaining ice. The pressure is minute by terrestrial standards, perhaps a few pascals, perhaps less, but it is sufficient to exert force on the fragile crust above. The crust, weakened by its own porosity, by microfractures accumulated over eons of thermal cycling and cosmic ray bombardment, begins to yield. Not everywhere, not uniformly, but in specific locations where the crust is thinnest or the subsurface pressure highest. Small ruptures open. Gas streams outward through these ruptures, carrying with it dust particles dislodged from the pore walls and entrained in the flow. The first jet is born, a column of carbon monoxide and dust accelerating away from the nucleus at speeds of hundreds of meters per second, expanding into the vacuum, scattering sunlight as it spreads into the surrounding space. From Earth, this manifests as a sudden brightening in the comet's coma, a localized enhancement in the cloud of material surrounding the nucleus. Telescopes record the change. Brightness increases by perhaps half a magnitude over the course of 20 minutes, then plateaus, then gradually declines as the gas disperses and the jet's activity wanes. The jet does not continue indefinitely. After an hour, perhaps two, the flow weakens, subsurface pressure has equalized, venting into space through the newly opened channel, or the rupture has sealed itself. Dust and ice fragments tumbling back to clog the opening, or the region of ice feeding the jet has depleted, leaving behind only refractory material that cannot sublimate at these temperatures. The exact mechanism remains uncertain, observed only through its effects on brightness and spectral emission, never directly imaged at the resolution needed to see individual vents opening and closing on a kilometer-scale nucleus millions of kilometers away. What is certain is that the jet stops, and the coma dims, and for several hours the comet appears quiescent once more. The nucleus continues its rotation. Best estimates suggest a period somewhere between 8 and 12 hours, though the ambiguity in this measurement is itself revealing. If the rotation was simple, If the nucleus spun around a single axis with active vents distributed symmetrically, the periodicity would emerge clearly from the data. The fact that it does not suggests either a complex rotation state or an irregular distribution of activity, or both. Hours pass, the nucleus turns, carrying different regions into sunlight. Heat continues its slow diffusion into the interior, now penetrating areas that were previously in shadow or had not yet accumulated sufficient energy to trigger sublimation. Another pocket of carbon monoxide ice reaches its sublimation threshold. Another accumulation of gas pressure. Another rupture in the crust. Another jet, but this one emerges from a different location on the nucleus, perhaps on the opposite hemisphere, perhaps oriented at a different angle relative to the sun. The resulting brightness increase differs from the first, stronger perhaps, or weaker, or lasting a different duration, because the geometry has changed, because the amount of available ice differs, because the thickness of the overlying crust varies from place to place. This second outburst is recorded in the brightness measurements as another peak. But when analysts attempt to phase-fold the data, a technique that averages measurements according to rotational period to reveal repeating patterns, the peaks do not align cleanly. The time interval between the first and second outburst is not a simple fraction of the presumed rotation period. A third outburst follows, then a fourth, each separated by intervals that seem almost but not quite regular, as if the comet were attempting to establish a rhythm but constantly falling out of sync with itself. Spectroscopic observations during these early outbursts reveal the dominance of carbon monoxide in the expelled gas. The emission lines at characteristic wavelengths, particularly the strong transitions in the ultraviolet and infrared, show intensities far exceeding those of water. This ratio is unusual. Comets born in our solar system typically show water as the primary volatile, with carbon monoxide present but subordinate, because water ice is stable across a wider range of distances from the Sun and dominates the composition of the protoplanetary disk in the regions where most comets formed. The abundance of carbon monoxide in 3I/Atlas speaks to formation in the outer reaches of its birth system, where temperatures dropped low enough for carbon monoxide to freeze out in large quantities, or possibly to formation around a star with a different chemical inventory than our Sun, enriched in carbon-bearing molecules. The asymmetry of the early jetting also becomes apparent in images of the coma. Rather than forming a symmetric halo around the nucleus, the gas and dust spread preferentially in certain directions, creating a lopsided appearance. One side of the coma glows brighter, denser with material, while the opposite side appears more tenuous. This suggests that the active vents are concentrated on one hemisphere, or that jets fire preferentially in certain directions due to the orientation of the ruptures in the crust. The coma's shape evolves over hours as the nucleus rotates and new jets activate, but the asymmetry persists, shifting in orientation but never resolving into uniform emission. Computer models of cometary activity struggle to reproduce this behavior. Standard models assume a spherical or ellipsoidal nucleus with a uniform surface composition, heated by sunlight according to simple geometric rules, outgassing in a pattern determined by the rotation rate and the sun's position. These models predict regular periodicity. They predict that brightness variations should repeat with each rotation. They do not predict the irregularity observed in 3I/Atlas, the offbeat rhythm that refuses to stabilize. Researchers adjust their models, introducing complexity. They allow for non-uniform distribution of volatiles beneath the surface, creating active and inactive regions. They introduce thermal inertia, allowing different parts of the crust to heat and cool at different rates. They experiment with tumbling rotation states, where the nucleus spins around a changing axis, making the pattern of solar heating more complicated. Some of these modifications improve the fit to the observations, but none capture the full irregularity. The comet's behavior suggests a level of internal heterogeneity, of structural complexity, that exceeds what current models easily accommodate. And yet, the irregularity is not chaos. There is structure in the brightness variations, hints of quasi-periodicities, intervals that recur more often than chance would predict even if they do not repeat exactly. It is as if the comet operates according to rules, but rules shaped by its particular history, by the specific arrangement of ices and voids and fractures within its interior. An arrangement unique to this object and perhaps unduplicable in any model that does not account for billions of years of evolution in interstellar space. The asymmetric breath continues, jet after jet, each slightly different. As 3I/Atlas approaches perihelion and the intensity of solar heating climbs toward its maximum, carbon monoxide's strange dominance reveals itself most clearly in the spectra captured during the comet's brightest phase. Astronomers directing telescopes toward 3I/Atlas in mid-January employ spectrographs that split the comet's light into its constituent wavelengths, revealing not just the brightness of the coma, but its chemical composition. Each molecule, when energized by sunlight or collisions, emits photons at specific frequencies determined by quantum mechanical transitions between energy states. These emission lines serve as fingerprints, allowing observers to identify which gases are present and in what abundance. The spectrum of 3I/Atlas shows carbon monoxide emission lines blazing with unexpected intensity. The fundamental vibrational band near 4.7 micrometers in the infrared, the rotational transitions in the millimeter wavelengths, the electronic transitions in the ultraviolet, all register strongly, indicating a production rate of carbon monoxide molecules streaming from the nucleus at rates approaching hundreds of kilograms per second during peak activity. Water lines are present, certainly, particularly the hydroxyl radical emission at 308 nanometers that marks water dissociation, but the ratio of carbon monoxide to water exceeds 10:1 during some measurements, far higher than typical for solar system comets. This ratio carries information about temperature. Carbon monoxide freezes at lower temperatures than water, approximately 25 Kelvin for pure carbon monoxide ice at near zero pressure, compared to roughly 150 Kelvin for water ice under similar conditions. In the protoplanetary disk around a young star, the region where carbon monoxide can condense extends much farther from the star than the region where water freezes. Close to the star, within a few astronomical units for a sun-like star, temperatures remain too high for either molecule to freeze. Farther out, beyond what is sometimes called the snow line, water begins to condense as ice. Farther still, beyond perhaps 30 or 40 astronomical units, depending on the specifics of the disk's temperature structure, carbon monoxide joins the solid phase. A comet rich in carbon monoxide relative to water must have incorporated a significant fraction of its ice in these outer regions, or formed in a disk where the temperature gradient differed from our solar systems, allowing carbon monoxide to dominate even at moderate distances. The abundance ratios in 3I/Atlas suggest formation temperatures around 20 to 30 Kelvin, conditions consistent with the outer reaches of a protoplanetary disk, or perhaps the even colder environment of a debris disk around a mature star. This is colder than the formation environment of most solar system comets, even those originating in the Oort cloud, which likely formed in the region of the giant planets and were subsequently scattered outward. The emission lines also reveal isotopic information, though this requires high-resolution spectroscopy and careful analysis to extract. Carbon monoxide molecules come in several isotopic varieties depending on which isotope of carbon and oxygen they contain. The most common form uses carbon-12 and oxygen-16, but rarer forms incorporate carbon-13 or oxygen-17 or oxygen-18. The ratios between these isotopic species reflect the chemical environment where the molecules formed, influenced by nuclear processes in stars, by mixing in the interstellar medium, by chemical fractionation during ice formation in cold molecular clouds. Initial measurements of the carbon and oxygen isotopic ratios in 3E/Atlas show values consistent with solar system abundances within the measurement uncertainties. But this is not particularly constraining. The solar system's isotopic composition itself derives from the interstellar material that collapsed to form the Sun and its disk, and much of the galaxy shares similar ratios, averaged over many stellar generations. Detecting a clear isotopic signature that would definitively mark 3I/Atlas as extrasolar in origin requires higher precision than most observations achieve, and the comet's rapid passage through the inner solar system limits the available observation time. What the carbon monoxide dominance does confirm, beyond doubt, is that this comet's history differs from objects native to our Sun's influence. No known solar system comet shows such extreme carbon monoxide enrichment, even Oort cloud comets, thought to preserve primitive compositions from the solar system's formation, typically show water as the primary volatile, with carbon monoxide contributing perhaps 10% or less of the total gas production. The only comparable objects are certain interstellar ices observed in molecular clouds through infrared absorption spectroscopy, where carbon monoxide ice mantles coat dust grains in regions of active star formation, and where temperatures hover between 10 and 20 Kelvin. This connection to molecular cloud chemistry provides a tentative narrative for 3I/Atlas's origin. Perhaps it formed in the outer disk of a star embedded in or recently emerged from a molecular cloud, a disk still rich in the same carbon monoxide ices that permeate the cloud itself. Or perhaps it formed later, in a debris disk produced by collisions among planetesimals, but in a system where carbon monoxide remained abundant far from the star. Or perhaps, and this remains speculative, it formed not in a circumstellar disk at all, but directly in interstellar space, condensing from a collapsing cloudlet too small to ignite fusion. A failed star whose remnant fragments now wander the galaxy as orphaned ice and rock. The mystery of such extreme compositional divergence from solar system norms raises questions about the diversity of planetary systems. If 3I/Atlas represents typical conditions in its birth environment, then that environment differs substantially from ours, colder, more carbon-rich, perhaps orbiting a star of different spectral type or at a different stage of evolution. Red dwarf stars, for instance, emit less ultraviolet radiation than Sun-like stars, which might allow carbon monoxide to persist in solid form at smaller distances from the star. Or perhaps the host star underwent periods of high luminosity during its early evolution, driving temperature fluctuations in the disk that influenced which ices condensed and where. No direct detection of the parent star is possible, even if 3I/Atlas's trajectory could be traced backward through the galaxy, accounting for the gravitational perturbations of every star and molecular cloud it passed during its interstellar journey. The uncertainties accumulate too quickly. After 1,000,000 years, the orbit becomes effectively unknowable. After 10,000,000 years, the region of origin expands to encompass hundreds or thousands of cubic parsecs, containing thousands of stars. The comet carries no return address, only the chemical signature of a place and time now inaccessible to direct observation. Yet the carbon monoxide continues to stream from the nucleus, indifferent to these questions of provenance. Each molecule that sublimates from the ice matrix, that accelerates through the crust's ruptures, that disperses into the coma and eventually dissociates under solar ultraviolet radiation, carries within its structure the memory of those formation conditions, the temperature at which it froze, the pressure at which the ice crystallized, the ratio of carbon-13 to carbon-12 established by nucleosynthesis in long-dead stars and modified by chemistry in the cloud from which both 3I/Atlas and its parent star condensed. The gas production rate varies with the irregular rhythm of the jetting. During quiescent periods, carbon monoxide emission drops to perhaps tens of kilograms per second. The coma, thinning as previously expelled gas, disperses faster than new material arrives. During outbursts, the rate spikes by factors of 3 or 5 or sometimes 10. The coma brightening and expanding, scattering more sunlight, becoming more prominent in images and more intense in spectroscopic measurements. These variations occur on timescales of hours, sometimes minutes, too rapid to be explained by changes in solar heating alone, which varies smoothly as the distance between comet and sun changes over days and weeks. The rapidity of the variations points again to the subsurface structure, to the opening and closing of vents, to the episodic release of gas from pockets of ice that accumulated pressure over hours before finding a path to the surface. Carbon monoxide, with its low sublimation temperature, responds quickly to even modest temperature changes. A warming of just a few degrees can shift regions from dormancy to activity, releasing gas that had remained stable moments before. This sensitivity makes carbon monoxide-rich comets like 3Y/Atlas particularly prone to irregular outbursts, each triggered by the particular thermal state of a particular pocket of ice at a particular moment. And so the spectrum continues to blaze with carbon monoxide lines. Each photon emitted a small testament to the comet's alien origin, a signal sent across the light minutes between nucleus and Earth, decoded by instruments sensitive enough to measure the wavelength shifts that reveal velocity, temperature, abundance, all the quantifiable properties that sketch the invisible processes occurring on and within a dark nucleus too small and distant to see directly. The missing periodicity haunts the analysis like an absence that should be filled. Astronomers expect comets to reveal their rotation through the rhythm of their light, through the dependable cadence of active regions turning into and out of sunlight as the nucleus spins. This expectation rests on decades of observation, on hundreds of comets tracked through their passages near the Sun, nearly all of which eventually yield to mathematical techniques designed to extract periodic signals from noisy data. 3I/Atlas resists these techniques with a stubbornness that suggests something fundamental about its structure or its motion defies the standard assumptions. The search for periodicity begins with photometry, continuous monitoring of the comet's brightness through filters that isolate specific wavelengths. Multiple observatories contribute data, some tracking the comet for hours each night, others capturing shorter sequences when weather or scheduling permits. The individual brightness measurements scatter around a mean value, as expected from photon counting statistics and atmospheric turbulence, but embedded within this scatter should be a signal, a repeating rise and fall tied to rotation. Fourier analysis. The mathematical decomposition of time series data into constituent frequencies should reveal this signal as a peak in the power spectrum, a frequency where brightness variations concentrate their energy. The power spectrum of 3I/Atlas shows multiple peaks, none dominant. One appears near a period of 10 hours, another near 12 hours, others at shorter and longer intervals. None of these peaks rises significantly above the noise floor with enough confidence to declare a definitive rotation period. Phase folding the data using any of these candidate periods produces light curves that show some structure. Brightness tends to be higher at certain phases, but the structure is weak, smeared, inconsistent from one rotation to the next. If the 10-hour period is correct, then brightness should peak at the same phase every 10 hours, but it does not. Sometimes the peak arrives early, sometimes late, sometimes barely appears at all. This could indicate a complex rotation state. Many small bodies in the solar system, asteroids, comet nuclei, small moons, do not spin simply around a single axis, but instead tumble, rotating simultaneously around multiple axes with different rates. In such cases, the orientation of the body relative to the Sun and to Earth changes in complicated ways, and the pattern of illumination and viewing geometry becomes correspondingly complex. Tumbling bodies can exhibit quasi-periodic light curves with multiple overlapping periods, making it difficult to isolate a single dominant frequency. Modeling tumbling rotation requires knowing the shape of the nucleus, which remains unknown for 3I/Atlas. The nucleus has never been resolved in images. Even the largest telescopes see only the coma, the cloud of gas and dust that obscures the solid body at its center. Shape determines how brightness varies with orientation. An elongated nucleus will appear brighter when viewed broadside and dimmer when viewed end-on, producing larger brightness variations than a more spherical nucleus. Without knowing the shape, models of tumbling rotation become under-constrained, able to fit almost any light curve by adjusting parameters. Alternatively, the missing periodicity might reflect not the nucleus's rotation state, but the distribution of active regions on its surface. If jets activate and deactivate irregularly, unconnected to rotational phase, then no clear period will emerge from the brightness variations. This scenario requires explaining why jets would behave so irregularly. One possibility involves the comet's approach trajectory and the changing angle of sunlight. As 3I/Atlas falls toward the sun, the subsolar point, the location on the surface where sunlight strikes most directly, traces a path across the nucleus that depends on both the comet's orbital motion and its rotation. If the subsolar point crosses regions of varying ice composition or crust thickness, different areas might activate at different solar distances, creating a pattern of jetting that changes over days or weeks, even if the rotation itself remains steady. Another possibility involves thermal inertia variations across the surface. Thermal inertia measures how quickly a material heats and cools in response to changing illumination. A surface with low thermal inertia, like loose dust or highly porous material, responds quickly to sunlight, warming rapidly when illuminated and cooling rapidly when shadowed. High thermal inertia materials, like dense ice or solid rock, change temperature more slowly. If the nucleus surface contains patches with different thermal inertias, those patches will reach sublimation temperatures at different times after sunrise, even if they rotate into sunlight simultaneously. This could produce jets that fire out of phase with rotation, obscuring the periodic signal. Deep beneath the photometry and the spectroscopy lies an uncomfortable truth. The comet may simply be too complex for current observational techniques to fully characterize. With only a few weeks of data before it fades, with brightness variations occurring on multiple overlapping timescales, with no spatially resolved images of the nucleus or its jets, analysts face an underdetermined inverse problem: too many unknowable parameters to fit, too little data to constrain them all. The rotation period, if it exists as a single well-defined value, hides within uncertainties. Some researchers propose that 3I/Atlas might be a contact binary, two lobes joined at a narrow neck, each potentially rotating at different rates or wobbling around their common center of mass. Contact binaries are known among solar system comets. 67P/Churyumov-Gerasimenko, visited by the Rosetta spacecraft, displayed this morphology clearly in high-resolution images. Such objects can exhibit complex rotation dynamics, with torques from outgassing gradually changing the spin rate or even causing the two lobes to separate entirely if activity concentrates at the neck region. But this remains speculation, no more constrained by data than any other hypothesis. The photometric record shows variability without clear periodicity. The spectroscopic record shows outbursts separated by irregular intervals. No model fits both datasets simultaneously while also remaining physically plausible. The rotation period, if it exists, remains missing, not because it is absent, but because the tools available to measure it prove insufficient to the task, or because the quantity being sought is itself ill-defined for an object as structurally complex as this one appears to be. Ironically, The first interstellar object detected, 1I/Oumuamua, also defied attempts to measure its rotation period definitively, though for different reasons. That object showed large brightness variations suggesting an extremely elongated shape, but the period measurements varied between different observing teams, and the object's non-gravitational acceleration, likely from outgassing too faint to detect directly, complicated the analysis. 2I/Borisov, the first confirmed interstellar comet, proved more cooperative, showing clear periodic variations tied to a rotation period near 9 hours. 3I/Atlas, the third visitor, returns to ambiguity. The missing periodicity becomes part of the comet's signature, part of what distinguishes it in the catalogue of interstellar objects. Where other comets reveal themselves through regular pulsing, through the clockwork predictability of spin, 3I/Atlas offers only irregular breathing, a rhythm that refuses to resolve into simple timekeeping. The data accumulates, brightness measurements every few minutes for hours each night, spectroscopic snapshots capturing composition and velocity, astrometric positions tracking the comet's motion against background stars. But the central question of rotation remains unresolved as the comet continues its outbound journey. Fading, carrying its secrets toward the outer solar system and eventually back into interstellar space where periodicities and rotations matter only to the ice itself. Unobserved, spinning or tumbling through the dark, subsurface architecture of ancient ice stretches beneath the dark crust in geometries shaped by 4 billion years of slow evolution. The interior of 3I/Atlas remains invisible to direct observation, accessible only through inference and modeling, through interpreting the surface phenomena, the jets, the outbursts, the irregular emission of gas, as symptoms of deeper structure. What lies beneath must be heterogeneous, porous, fractured, layered, a three-dimensional maze of ice and void and dust assembled grain by grain in some distant protoplanetary disk and modified by every subsequent event in the comet's history. Formation begins with accretion. In the outer regions of a circumstellar disk, where temperatures hover near 20 or 30 Kelvin, microscopic ice-coated dust grains drift through dilute gas, colliding occasionally at velocities of meters per second or less. Some collisions result in sticking, electrostatic forces or sintering binding particles together into aggregates. These aggregates grow slowly, accumulating more grains, forming irregular clumps that themselves collide and merge, over time scales of thousands or millions of years, depending on the density of the disk and the efficiency of sticking. These clumps grow from millimeters to meters to kilometers, eventually reaching sizes large enough that self-gravity begins to matter. The resulting body is not a solid monolith, but a gravitational aggregate, a rubble pile held together by its own weak gravity and by the cohesion between ice grains. Porosity is high, perhaps 50% or more by volume, meaning that half the comet's volume consists of empty space, voids between and within the aggregated clumps. This porosity varies with depth. Near the surface, where impacts and thermal cycling can disrupt the structure, porosity may be even higher, creating a loose regolith of dust and ice fragments. Deeper inside, gravitational compaction reduces porosity slightly, but the material remains far less dense than solid ice, far more like a frozen sponge than a frozen ocean. Within this porous matrix, different ices distribute themselves according to their condensation histories. Carbon monoxide, condensing at the lowest temperatures, may have frozen onto grain surfaces first, forming the innermost layers of ice mantles. Water, requiring slightly warmer conditions, may have condensed later, coating the carbon monoxide. Other volatiles, carbon dioxide, methane, ammonia, molecular nitrogen, each found their place in the mantle structure according to their sublimation temperatures and their abundances in the surrounding gas. The result is a compositional stratigraphy at the scale of individual grains, layers mere nanometers thick, recording the thermal history of the disk during accretion. But the comet is not homogeneous even at larger scales. Different regions of the protoplanetary disk possess different temperatures, different compositions, different dust-to-gas ratios. As the growing nucleus swept up material from its surroundings, it incorporated ices that formed under slightly different conditions, creating domains within the interior where one volatile dominates over others. Perhaps one region formed from material rich in carbon monoxide, another from material where water ice was more abundant. These domains, once incorporated into the growing body, became frozen into place. Their boundaries determined by the stochastic nature of low-velocity collisions and gravitational settling. Over billions of years in interstellar space, this structure evolves through processes both subtle and slow. Cosmic rays, high-energy protons and atomic nuclei streaming through the galaxy, penetrate the nucleus, colliding with molecules in the ice, breaking chemical bonds, creating radicals and new molecular species. Amorphous ice, the disordered form in which water freezes at very low temperatures, gradually transitions to crystalline ice, a process driven by energy deposited by cosmic rays and by radioactive decay of trace elements embedded in the dust. This crystallization releases latent heat and can trigger localized sublimation even in the cold of interstellar space, creating tiny voids where gas escapes and refreezes elsewhere. Slowly redistributing material within the interior, impacts by interstellar dust grains, rare but inevitable over millions of years, fracture the surface and subsurface layers, creating cracks that extend centimeters or meters into the interior. These cracks provide pathways for gas to escape during future sublimation events, pre-weakening the structure in patterns that depend on the random timing and geometry of impacts. Each fracture slightly alters the mechanical properties of the crust, making some regions more resistant to rupture and others more prone to failure when internal pressure builds. Differential thermal expansion also plays a role, though subtle. Even in interstellar space, the nucleus experiences temperature variations as it passes through regions of varying interstellar radiation field intensity or as it drifts through molecular clouds where temperatures drop even lower than the ambient cosmic microwave background floor. Different ices have different coefficients of thermal expansion. They expand and contract by different amounts for the same temperature change over many thermal cycles. This creates internal stresses, microscopic cracks at boundaries between ice types, gradual weakening of cohesion. By the time 3I/Atlas enters the solar system, its interior is a palimpsest of these processes, an archive of events recorded in structural discontinuities, compositional boundaries, porosity variations, fracture networks. This architecture determines where and when jets will form as solar heating penetrates inward. A pocket of carbon monoxide ice trapped beneath a particularly thick layer of dust-rich crust may remain dormant until the comet passes very close to the Sun, only then accumulating enough pressure to rupture through. Another pocket, beneath thinner crust or connected to the surface by a network of pre-existing fractures, might activate at larger distances, releasing gas in a sustained jet that persists for hours. The irregularity of outbursts reflects this heterogeneity. Each jet tells the story of a particular subsurface volume with its particular composition, its particular depth, its particular connection to the surface. Jets do not repeat precisely because the subsurface reservoir feeding each jet is unique, depleted after one outburst, requiring time to accumulate fresh gas from neighboring regions through slow diffusion of heat and pressure equilibration. The comet's interior is not a uniform reservoir that can be tapped repeatedly in the same way, but rather a collection of distinct pockets, each with its own threshold for activation and its own supply of volatile material. Models attempting to simulate this complexity divide the interior into cells or voxels, each assigned properties like ice composition, porosity, thermal conductivity, mechanical strength. Heat diffusion equations govern how temperature evolves within each cell as sunlight warms the surface. Sublimation occurs when cells reach critical temperatures, producing gas that must flow through the porous matrix to reach the surface. The simulation tracks gas pressure within the voids, rupture of crust when pressure exceeds strength, outflow through newly opened channels. These models capture some aspects of the observed behavior: irregular outbursts, varying intensities, preferential jetting from certain regions, but require assumptions about initial conditions, about the distribution of ice types, about mechanical properties, all of which remain unconstrained by observations. The subsurface architecture of 3I/Atlas will never be known directly. No spacecraft will land on this comet. Drill into its interior, measure its properties in situ. The comet is already fading, already receding, and its hyperbolic trajectory ensures it will not return. The interior remains a theoretical construct, inferred from surface phenomena, modeled through simulations that can match observations only by invoking structures complex enough to accommodate irregularity. Somewhere within that hidden interior, chambers of ancient ice wait in geometries determined by processes billions of years old, geometries that shaped every jet observed from Earth, geometries that will continue to evolve as the comet returns to the cold, slowly sublimating from residual internal heat, slowly annealing, slowly erasing the evidence of its brief encounter with our sun. Thermal lag and delayed eruptions emerge as central characters in the narrative of irregular jetting, though they operate invisibly, measurable only through their effects on timing and brightness. The phenomenon begins with sunlight striking the surface, delivering energy that must then propagate inward through layers of ice and dust before reaching depths where sublimation can occur. This propagation is not instantaneous. Heat moves through solid matter by conduction, a process governed by thermal diffusivity, a quantity that depends on thermal conductivity, density, and specific heat capacity. For porous, dusty ice like that composing 3I/Atlas's crust, thermal diffusivity is low, meaning heat diffuses slowly, taking hours to penetrate even a few centimeters. The mathematics of heat diffusion describes this delay precisely. The thermal diffusion length, the depth to which a periodic temperature variation penetrates before being attenuated, scales with the square root of the period and the thermal diffusivity. For diurnal temperature variations driven by a 10-hour rotation period, and assuming thermal diffusivities typical of porous cometary material, the diffusion length reaches only a few centimeters. Heat from sunlight warming the surface during the nucleus's dayside hours penetrates to this depth before the rotation carries that surface region back into shadow and cooling begins. Deeper layers remain thermally isolated, warming only through the gradual accumulation of heat from many rotation cycles or from sustained heating as the comet approaches perihelion and solar distances decrease. This creates a temporal disconnect between illumination and sublimation. A region of the surface rotates into sunlight at some moment, call it time zero. The surface itself warms quickly, perhaps reaching maximum temperature within an hour as it absorbs sunlight and re-radiates infrared. But the subsurface, centimeters below, remains cold. Still at the temperature established hours earlier, heat begins flowing downward through conduction, warming each successive layer with a delay that increases with depth. A layer 1 centimeter deep might reach its maximum temperature 2 hours after surface sunrise, a layer 3 centimeters deep. 4 hours later, by the time heat reaches depths where significant carbon monoxide ice resides, perhaps 5 or 10 centimeters below the surface, beyond the desiccated crust depleted of volatiles by previous sublimation, many hours have passed, and the surface above may have already rotated back into shadow. Jets. therefore can fire long after the region feeding them has left sunlight. An observer watching the comet from Earth sees an outburst begin, brightness increasing, gas emission intensifying. If they attempt to correlate this outburst with the nucleus's rotational phase, assuming the active region is currently facing the Sun, they will be mistaken. The active region fired hours ago. Solar noon hours in the past for that particular patch of surface. The jet erupts from heat delivered earlier, from energy that penetrated inward during the region's illuminated hours and only now, belatedly, reaches depth sufficient to trigger sublimation. This lag varies across the nucleus depending on local properties. Regions where the crust is thinner or less insulating allow heat to penetrate more quickly, producing jets with shorter delays between illumination and outburst. Regions where thick layers of dust or refractory material overlie the ice show longer lags, erupting many hours after sunrise or not erupting at all if insufficient heat penetrates before sunset cools the surface again. Variations in porosity also matter. Higher porosity means lower thermal conductivity, slower heat propagation, longer lags. The heterogeneous interior structure guarantees that different locations experience different lag times, destroying any simple correlation between rotational phase and jetting activity. Complicating matters further. Heat does not only flow inward, but also sideways through lateral conduction. A patch of surface in full sunlight warms not only the material directly beneath it, but also adjacent regions, creating temperature gradients that drive heat flow in 3 dimensions. If a pocket of volatile ice lies not directly beneath an illuminated surface, but slightly to the side, heat may reach it through sideways diffusion, triggering a jet at a location offset from the apparent subsolar point. This 3-dimensional heat flow is difficult to model accurately without knowing the detailed geometry of ice pockets and thermal conductivity variations, introducing additional uncertainty into predictions of where and when jets will appear. The delayed eruptions also affect the momentum imparted to the nucleus by outgassing. When jets fire, the expelled gas carries momentum, exerting a reaction force on the nucleus, the rocket effect. For a symmetric comet with jets firing from the subsolar point, this force would push directly away from the Sun, slightly altering the comet's trajectory, but in a predictable manner. For 3I/Atlas, with jets firing at irregular times and from locations offset from the instantaneous subsolar point due to thermal lag, the rocket effect becomes more complex. Forces act in directions that depend on the particular geometry of active vents at the moment of outgassing, creating torques that can change the nucleus's rotation state, as well as translational forces that alter its orbit in ways not easily predicted. Measurements of 3I/Atlas's position against background stars, astrometry, reveal small deviations from the purely gravitational trajectory predicted by considering only the Sun's gravity and the perturbations from planets. These non-gravitational accelerations are typical of active comets and attributed to outgassing, but quantifying them precisely requires knowing when and where jets fire, information that remains incomplete for an irregularly active comet with no resolved images of the nucleus. Analysts attempt to model the non-gravitational forces by fitting parameters to the observed trajectory, but the solutions are non-unique. Multiple combinations of jet orientations and activity levels able to produce similar astrometric signatures. The thermal lag also influences the long-term evolution of the comet's surface. Regions that experience repeated sublimation develop a mantle of dust and refractory material left behind as ice sublimates. Volatile molecules escape into space while heavier particles, too massive to be lifted by the weak gas flow, settle back onto the surface. This mantle builds up over time, increasing the thickness of the insulating layer, lengthening the thermal lag for that region, possibly shutting off jetting entirely if the mantle becomes thick enough to prevent heat from reaching remaining ice deposits below. Different regions mantle at different rates, depending on the dust-to-ice ratio in their subsurface material and the intensity of jetting they experience, creating a feedback loop where active regions gradually deactivate and new regions previously dormant become active as the comet's thermal environment evolves. In this way, thermal lag becomes not just a delay, but a shaping force, determining which regions of the nucleus contribute to jetting at which times during the comet's passage, sculpting the pattern of activity through the interplay of heat flow, sublimation, and mantle formation. The irregularity observed in 3 I/Atlas's light curve may reflect this dynamic evolution, the comet transitioning through different activity states as some vents shut down and others open, each change governed by the slow conductive transfer of heat through centimeters of porous ice. No direct measurement of thermal lag is possible for 3 I/Atlas. The timing of jets relative to illumination cannot be determined without knowing the rotation period and the locations of active regions on the surface, both of which remain uncertain. Instead, the presence of lag is inferred from the absence of clear rotational periodicity, from the mismatch between simple models and observations, from the theoretical expectation that low thermal conductivity materials must exhibit such delays. The lag hides in the data's noise, in the scatter of brightness measurements, in the irregular spacing between outbursts, present but not directly visible, an invisible process leaving visible effects. The coma's asymmetric glow manifests in images as a lopsided halo surrounding the unresolved nucleus, brighter on one side, dimmer on the other, sometimes exhibiting streamers or jets extending preferentially in specific directions. This asymmetry develops as gas and dust expelled from the nucleus expand into the surrounding space, scattering sunlight and creating the diffuse cloud that makes the comet visible to telescopes on Earth, unlike the nucleus, which remains a point source even in the largest telescopes due to its small angular size at millions of kilometers distance. The coma spreads across seconds or minutes of arc, providing spatial information about how material distributes itself around the comet. The shape of the coma depends on multiple factors: the distribution of active regions on the nucleus, the velocity and direction of material ejection, the interaction of expelled gas with solar radiation pressure and the solar wind, and the viewing geometry from Earth. For 3 I/Atlas, images taken during its brightest phase in mid-January show the coma extending asymmetrically, with one side reaching farther from the nucleus and appearing brighter in surface brightness measurements. This suggests that jets preferentially fire in certain directions, ejecting more material toward one side than the other. Gas and dust leave the nucleus at velocities determined by sublimation physics and the local gravitational field. Carbon monoxide sublimating from ice accelerates through the porous crust, reaching velocities of several hundred meters per second by the time it emerges into vacuum, faster than water vapor would achieve under similar conditions because carbon monoxide molecules are lighter and thus accelerate more readily in pressure-driven flow. Dust particles entrained in this gas flow experience drag forces that accelerate them upward, though they reach lower terminal velocities than the gas due to their greater mass. Typical dust velocities in cometary comae range from tens to hundreds of meters per second, depending on particle size and gas production rate. Once free of the nucleus, this material expands outward, forming the coma. The gas expands nearly radially, slowed slightly by collisions with other gas molecules near the nucleus, where densities remain relatively high, but quickly transitioning to ballistic trajectories as density drops and the mean free path between collisions exceeds the scale of the coma. Dust particles, already on ballistic trajectories once drag forces from the gas become negligible, continue outward along straight lines determined by their ejection velocity and the weak perturbations from solar radiation pressure. Solar radiation pressure affects particles differently depending on their size. Very small particles, submicron to micron scale, experience strong radiation pressure, accelerating anti-sunward and forming dust tails that extend for millions of kilometers behind the comet. Larger particles, millimeter scale and above, are less affected, their greater mass making them less responsive to photon momentum transfer. They follow trajectories closer to purely ballistic expansion, creating more symmetric structures around the nucleus. The size distribution of dust particles expelled by 3y/Atlas determines how quickly the dust coma becomes elongated in the anti-sunward direction, with smaller particles sweeping back faster than larger ones. Imaging the coma at different wavelengths reveals different aspects of its structure. Broadband optical images, integrating light across the visible spectrum, show primarily scattered sunlight from dust particles, with some contribution from fluorescence emission from gas molecules. Narrowband images taken through filters isolating specific emission lines, such as the cyanide radical at 388 nanometers or the hydroxyl radical at 308 nanometers, show the distribution of particular molecular species in the coma, which may differ from the dust distribution if gas and dust decouple after ejection. For 3I/Atlas, narrowband images in carbon monoxide emission lines would show the gas coma, but such observations require instruments sensitive in the ultraviolet or infrared where carbon monoxide's strongest transitions occur. And not all observing campaigns acquired such data. The available optical images show mainly dust scattering, revealing an asymmetric structure consistent with jets firing from a limited number of active regions on the nucleus rather than uniform outgassing from the entire surface. The asymmetry evolves over hours and days as the nucleus rotates and as different jets activate. Time series imaging, if conducted with sufficient cadence, would show the bright side of the coma shifting in position angle as the orientation of active regions changes relative to the Sun-comet line. However, the evolution is complicated by the fact that material already in the coma continues expanding outward for hours after ejection. So the coma at any given moment represents an integrated history of jetting activity over the past several hours, not just the instantaneous state of the nucleus. Modeling the coma requires simulating the trajectories of millions of dust particles and following the hydrodynamics of gas expansion, computationally intensive work that becomes more complex when jetting is irregular. Standard coma models assume either uniform outgassing or a small number of discrete jets firing continuously, allowing for solutions that can be computed efficiently. 3I/Atlas's behavior, with multiple jets activating and deactivating on irregular schedules, requires time-dependent models where the source terms change every few hours, significantly increasing computational demands. Some researchers attempt to invert the problem, given the observed coma morphology. Can one deduce the locations and orientations of active regions on the nucleus? This is an inverse problem, notoriously difficult because the mapping from source to observation is non-unique. Many different configurations of jets can produce similar-looking comae depending on viewing geometry, particle size distribution, gas-to-dust ratio, and the timing of ejection events. Without independent constraints on the rotation state and surface properties, the inversion remains under-constrained. Nonetheless, the asymmetry provides clues. The fact that one side of the coma consistently appears brighter suggests that active regions are not distributed uniformly around the nucleus, but concentrated in specific areas, likely one hemisphere. This could result from compositional heterogeneity, one hemisphere richer in volatiles than the other, or from differences in surface properties like albedo or thermal inertia that affect how efficiently sunlight heats the subsurface. Compositional hemispheric dichotomies are known among solar system comets. Some nuclei show stark differences in activity between their northern and southern hemispheres, possibly reflecting formation in a stratified protoplanetary disk or subsequent collisional events that preferentially altered one side. The streamers occasionally visible extending from the coma represent collimated jets seen nearly edge-on, where the material density along the line of sight integrates to produce higher brightness than in surrounding regions. These streamers can extend tens of thousands of kilometers from the nucleus, gradually fading as the material disperses and becomes too diffuse to scatter significant light. Their curvature, if measurable, provides information about the ejection velocity and the influence of solar radiation pressure. Faster ejection or weaker radiation pressure produces straighter streamers, while slower ejection or stronger radiation pressure curves them more sharply anti-sunward. The asymmetric glow, though striking in images, represents only the visible manifestation of processes occurring on and within the nucleus. The coma is secondary, a consequence, the debris of sublimation and ejection rendered visible by sunlight. Its brightness and structure change in response to the hidden rhythms of the nucleus, expanding when jets fire intensely, fading when activity wanes, shifting in orientation as rotation carries new regions into view. In this way, the coma serves as a proxy, an observable phenomenon that encodes information about the unobservable nucleus, allowing observers billions of kilometers away to infer something about the state of a body too small and dark to see directly. A body whose only voice is the gas and dust it releases into the light. Dust grains as timekeepers enter the narrative through their interaction with sunlight, through the way they scatter photons and thereby reveal their presence and their motion. Each grain expelled from the nucleus carries information encoded in its trajectory, its size, its composition, properties that determine how brightly it shines and how quickly solar radiation pressure pushes it anti-sunward. By measuring these properties through photometry and polarimetry, by analyzing the color and intensity of scattered light, researchers can work backward to infer when and how the grains were ejected, using them as markers in time to reconstruct the history of jetting events. The process begins with ejection. During an outburst, gas streaming from a vent drags dust particles upward from the surface or from the walls of subsurface pores, accelerating them through the crust until they emerge into vacuum. The acceleration depends on the gas velocity and density, on the particle's cross-sectional area and mass, on the duration of exposure to the gas flow. Smaller particles with higher surface area to mass ratios couple more efficiently to the gas and reach higher velocities. Larger particles, heavier and less responsive to drag, emerge more slowly or not at all if gas velocities are insufficient to overcome their weight in the nucleus's weak gravity. Once free of the gas flow, particles enter free fall, or more precisely, free drift under the combined influence of the nucleus's gravity, solar gravity, and radiation pressure. The nucleus's gravity is negligible beyond a few kilometers. For a kilometer-sized body, the escape velocity is only a few meters per second, easily exceeded by ejection velocities. Solar gravity acts uniformly on all particles regardless of size, producing no relative motion. Radiation pressure, however, depends on particle size and composition in complex ways described by Mie scattering theory, creating size-dependent accelerations that cause the dust cloud to spread and sort itself by grain size as it expands. Small particles, submicron to a few microns in radius, experience radiation pressure forces that exceed solar gravity, accelerating anti-sunward and forming the dust tail. Their acceleration is approximately constant once they leave the nucleus's immediate vicinity, so their trajectories become parabolic or hyperbolic curves pointing away from the sun. Medium-sized particles, tens of microns in radius, experience weaker radiation pressure, following trajectories that curve more gently. Large particles, hundreds of microns and above, are minimally affected, expanding outward nearly radially from the nucleus. This size-dependent sorting creates spatial structure in the dust coma, close to the nucleus. All sizes mix together, recently ejected and not yet significantly separated by radiation pressure. Farther out, the coma becomes stratified, with smaller particles concentrated in the anti-sunward direction and larger particles distributed more symmetrically. The rate at which this sorting proceeds depends on the strength of radiation pressure, which in turn depends on heliocentric distance. Radiation pressure scales inversely with the square of the distance from the Sun, so sorting happens faster when the comet is near perihelion. Measuring the brightness of different regions within the coma, and how that brightness changes with time, allows estimation of when particles were ejected. Consider a jet that fires at some specific time, releasing a cloud of dust. This cloud expands outward, its particles following trajectories determined by their ejection velocities and radiation pressure accelerations. Observing the coma some hours later, the dust from this jet has dispersed into a feature, perhaps a streamer or an enhancement in surface brightness at some distance from the nucleus. The position and extent of this feature depend on how long ago the jet fired and how fast particles were moving. By modeling particle trajectories and comparing to observations, researchers can estimate the ejection time. This technique works best when jets are discrete events well separated in time, producing distinct features in the coma that can be tracked individually. For 3I/Atlas. With multiple overlapping jets and irregular activity, the analysis becomes more difficult. The coma at any moment contains dust from several recent outbursts, their contributions blended together into a single observed brightness distribution. Disentangling the contributions requires modeling. Assumptions about particle size distributions and ejection velocities, iterative fitting procedures that search for the combination of source parameters that best reproduces the observations. Polarimetry adds additional constraints. Dust grains scatter sunlight polarimetrically. The scattered light becomes partially polarized, with the degree and direction of polarization depending on the scattering angle, particle size, composition, and shape. Measurements of polarization across the coma can reveal the dominant particle sizes in different regions, because small particles produce different polarization signatures than large particles. Polarimetric observations of 3I/Atlas, if conducted, would show variations in polarization degree corresponding to regions dominated by different grain sizes, potentially revealing the structure of individual dust jets. Color measurements provide yet another dimension. Dust grain scattering efficiency depends on wavelength, with the wavelength dependence determined by particle size and composition. Very small particles scatter blue light more efficiently than red light, making regions dominated by submicron grains appear bluer. Larger particles scatter more neutrally across the visible spectrum, appearing grayer or redder depending on composition. Mapping the color across the coma reveals how particle size distributions vary spatially, which in turn constrains ejection models. For 3I/Atlas. Photometric monitoring shows that the dust production rate, inferred from the total brightness of the coma after accounting for gas emission, varies in concert with the gas production rate, increasing during outbursts and declining during quiescent periods. This correlation suggests that dust and gas eject together, driven by the same sublimation events. Though the dust-to-gas mass ratio remains uncertain without direct measurements of both components simultaneously, some comets are dust-rich, ejecting many times more mass in dust than in gas. Others are dust-poor, with gas dominating the mass loss. The ratio affects the dynamics of ejection and the appearance of the coma, but determining it requires comparing gas production rates from spectroscopy with dust production rates from photometry, both subject to significant uncertainties. The dust grains themselves carry compositional information. Spectroscopic observations in the infrared can detect emission features from silicate minerals heated by sunlight, features near 10 and 18 micrometers wavelength that reveal whether the dust contains crystalline or amorphous silicates, olivine or pyroxene, iron-rich or magnesium-rich compositions. These features, when detected in cometary spectra, provide clues about the temperature and pressure conditions under which the dust formed, about processes in the protoplanetary disk that created and modified the grains before they accreted into the comet. For 3 I/Atlas, infrared spectroscopic observations during its brightest phase might have revealed such features, but the comet's rapid passage and relative faintness limited the available observing time with the largest infrared telescopes. If silicate features were detected, they could be compared with those from solar system comets to assess whether the dust composition shows any signatures of extrasolar origin, differences in the crystalline to amorphous ratio, or in the relative abundances of different silicate minerals, might indicate formation conditions distinct from those in our solar system's disk. Even without detailed spectroscopy, the color of the dust provides crude compositional constraints. Reddish dust suggests the presence of organic materials or iron-bearing minerals. Neutral gray dust indicates compositions dominated by silicates with low iron content. Observations of 3 I/Atlas show dust color consistent with solar system comets, slightly red, not dramatically so, suggesting that whatever differences exist between the comet's formation environment and our own did not produce drastically different dust composition, at least not at the level detectable in broadband color measurements. The temporal evolution of dust features in the coma serves as the most direct application of using dust as timekeepers. By imaging the comet repeatedly over hours or days and tracking how specific brightness enhancements move outward from the nucleus, researchers can measure expansion velocities and extrapolate backward to determine ejection times. This technique, sometimes called coma morphology analysis, has been applied successfully to many comets, revealing details of jetting activity that would otherwise remain hidden. For 3 I/Atlas, attempts at such analysis face challenges from the comet's distance and faintness, which limit spatial resolution and signal-to-noise ratio in images. Features in the coma appear as subtle brightness enhancements rather than sharply defined structures, making them difficult to track reliably over time. Nonetheless, some analyses identify apparent streamers or arcs in the coma that likely correspond to discrete ejection events, though the timing uncertainties remain large, several hours rather than the minute scale precision achievable for brighter, closer comets, the dust grains. Once ejected, continue their outward journey for weeks or months, gradually fading as they disperse and their number density drops below detectability thresholds. The largest particles, least affected by radiation pressure, may remain near the comet's orbital path, forming a debris trail that could potentially be detected years later if another object passes through the same region of space. Smaller particles sweep anti-sunward, eventually escaping the inner solar system entirely or spiraling into the sun under pointing Robertson drag, an effect where radiation pressure and aberration combine to remove orbital energy, causing particles to migrate slowly sunward over time scales of thousands to millions of years. In this way, the dust from 3 I/Atlas disperses into the solar system, mixing with dust from countless other comets, becoming part of the zodiacal cloud, the diffuse glow visible in dark skies before dawn or after sunset, caused by sunlight scattering from interplanetary dust, a tiny fraction of interstellar material, delivered by this comet and others like it, joins the predominantly solar origin dust that fills the inner solar system. The contribution is negligible in mass, but significant in what it represents: matter from other stellar systems mixing into our own. Cross-contamination between stars separated by light years. A slow exchange of material mediated by the occasional visitor passing through. Fragmentation signatures without breakup appear in the spectroscopic data as subtle hints of internal stress, as anomalies in the emission line profiles that suggest the nucleus experiences forces approaching the limits of its structural integrity, yet somehow holds together through each violent release of gas. Cometary fragmentation is not uncommon. Many comets observed throughout history have split into multiple pieces, sometimes gradually shedding fragments over weeks or months, sometimes disintegrating catastrophically within hours. The causes vary: tidal stress during close approaches to planets or the Sun, rotational spin-up from asymmetric outgassing creating centrifugal forces that exceed the nucleus's tensile strength, or thermal stress from rapid heating, cracking the ice and disrupting cohesion. For 3I/Atlas, observations show no clear evidence of fragmentation in the sense of separate nuclei visible in high-resolution images. The coma remains consistent with a single central condensation rather than multiple fragments moving apart. Yet, spectroscopic analysis reveals line profiles that deviate slightly from the Gaussian shapes expected for gas expanding isotropically from a single point source. The carbon monoxide emission lines, when examined at high spectral resolution, show asymmetries, secondary peaks, broadenings that suggest multiple velocity components in the expanding gas. These features could indicate several phenomena. One possibility is that gas ejects from multiple active regions with different orientations, creating components with different Doppler shifts as material streams toward and away from Earth at slightly different velocities. Another possibility involves shock waves in the expanding gas, regions where fast-moving material overtakes slower material, creating compression fronts that alter the velocity distribution and thus the emission line shapes. A third possibility, more concerning from a structural standpoint, is that the nucleus has developed large cracks or fissures that penetrate deep into the interior, creating separate chambers that outgas semi-independently, each contributing its own velocity signature to the total emission. The latter scenario approaches fragmentation without quite reaching it. A nucleus with deep internal fractures behaves mechanically as multiple pieces held together by weak cohesion or residual ice bridges, rather than as a monolithic body. Such a configuration is unstable. Further stress from outgassing or rotation or thermal expansion could widen the fractures, separate the pieces entirely, producing observable fragmentation. That 3I/Atlas shows signs of such stress, yet remains intact, suggests either that the cohesive forces just barely exceed the disruptive forces, a precarious balance, or that the fractures have not yet propagated fully through the nucleus. Theoretical models of cometary structure predict that tensile strength for ice dust mixtures, like those composing comet nuclei, is low, perhaps only tens to hundreds of pascals, comparable to the strength of freshly fallen snow. This weakness makes nuclei vulnerable to disruption. The forces acting to disrupt them include internal gas pressure from sublimation, which exerts stress on the surrounding ice as gas tries to escape, centrifugal forces from rotation, which pull material outward, especially at the equator of a spinning body, and thermal stress from differential expansion, which creates strain when some regions heat and expand while adjacent regions remain cold and contracted. Measurements of rotational state, though ambiguous for 3I/Atlas, suggest rotation periods in the range of 10 hours for a kilometer-sized nucleus. This corresponds to equatorial velocities of roughly 10 centimeters per second, slow by everyday standards, but sufficient to generate centrifugal accelerations that, while small, are not negligible compared to the nucleus's weak self-gravity. If outgassing additionally exerts torques that spin up the rotation over time, the centrifugal forces grow, potentially reaching levels that could separate loosely bound fragments. The outbursts themselves create transient stresses. When gas erupts from a subsurface pocket, the sudden pressure release can induce shock waves in the surrounding ice, propagating fractures outward from the vent. Repeated outbursts from the same region might progressively weaken the structure. widening cracks, reducing cohesion, preparing the nucleus for eventual fragmentation even if that event occurs years or centuries later, long after the comet has returned to interstellar space. Some solar system comets show what researchers call splitting events, where small fragments separate from the main nucleus but remain gravitationally bound, orbiting around the primary for days or weeks before either re-impacting the surface or escaping entirely. These events are often triggered by specific outbursts or by perihelion passage when thermal stress peaks. Searching for such fragments around 3I/Atlas requires high-resolution imaging to detect faint condensations near the nucleus, observations that are challenging given the comet's distance and the brightness of the surrounding coma. No fragments have been definitively detected, but the observations may simply lack the sensitivity to see small pieces that could nonetheless be present. Spectroscopic monitoring over time shows that the emission line anomalies persist, not growing significantly worse, but not disappearing either. This suggests a stable or quasi-stable configuration. Whatever structural issues exist within the nucleus are neither healing nor catastrophically worsening during the observed period. The nucleus continues to outgas, continues to show irregular jetting, continues to hold together despite the internal stresses implied by the spectroscopic signatures. One wonders about the nucleus's history, about whether it has always been on the verge of fragmentation, or whether this is a recent development triggered by the current passage through the inner solar system. In interstellar space, where temperatures are cold and sublimation negligible, cometary nuclei experience minimal stress. They drift in a frozen, static state, changing only through the slow processes of cosmic ray bombardment and occasional interstellar dust impacts. Structural weaknesses might develop gradually over billions of years, microcracks accumulating, cohesion degrading, but without the stresses of outgassing to propagate these weaknesses into macroscopic fractures. Entering a stellar system changes everything. Solar heating triggers sublimation, gas pressure builds, forces act on weakened structures. A nucleus that survived billions of years in interstellar space intact might fragment during its first perihelion passage, unable to withstand the stresses of activity. Alternatively, if the nucleus has passed through other stellar systems before, if 3I/Atlas is not on its first stellar encounter but has wandered through the galaxy long enough to pass near other stars, it may have experienced previous episodes of activity that already weakened it, that created the fractures now evident in spectroscopic signatures. The question of how many stellar encounters an interstellar comet experiences during its lifetime is an open one in galactic dynamics. The spacing between stars in the solar neighborhood is such that close approaches, within a few hundred astronomical units, close enough to trigger significant cometary activity, occur rarely, perhaps once every few million years on average for a comet wandering randomly through the galactic disk. Over 1 billion years. A comet might experience hundreds of such encounters, each potentially triggering outgassing, each potentially inducing structural damage. The cumulative effect could leave the nucleus fractured and weakened by the time it reaches our solar system. Yet the nucleus has not yet fragmented, at least not observably. It continues its outbound journey, jetting irregularly, shedding gas and dust, structurally stressed but intact. Perhaps it will survive this passage and return to the calm of interstellar space, fractures and all, to drift for another epoch until the next stellar encounter. Or perhaps the stresses will accumulate, cracks will widen, and at some future time, perhaps months or years from now, when the comet is far beyond observation, the nucleus will finally split, separating into pieces that will then continue independently, their orbits diverging slowly, each carrying a fraction of the original body's mass and history into the dark. Comparing the rhythm to 2I/Borisov provides context for understanding 3I/Atlas's peculiarities. for assessing whether its irregular behavior represents an extreme within the spectrum of cometary variability or signals something fundamentally different about its nature or origin. 2I/Borisov, discovered in August 2019 and designated the first confirmed interstellar comet, became the subject of intensive observational campaigns as it passed through the inner solar system, accumulating a dataset against which later interstellar visitors can be compared. 2I/Borisov displayed behavior that, while active and producing substantial gas and dust emission, followed patterns familiar from solar system comets. Photometric monitoring revealed a clear rotation period near 9 hours, evidenced by regular brightness variations that repeated with clockwork precision. The light curve showed a double-peaked structure within each rotation cycle, suggesting an elongated nucleus with two broad sides that alternately rotated into view, each producing a brightness maximum as its larger cross-section faced Earth. This periodicity persisted throughout the observing campaign, stable and reliable, allowing researchers to confidently determine rotation rate and constrain nucleus shape. Spectroscopic observations of 2I/Borisov showed carbon monoxide emission, as does 3I/Atlas, but in lower abundance relative to water. The carbon monoxide to water ratio for 2I/Borisov fell within the range observed for solar system comets originating in the Oort cloud, elevated compared to Jupiter family comets that form closer to the Sun, but not dramatically anomalous. This suggested that while 2I/Borisov originated in another stellar system, its formation conditions may have been broadly similar to those in the outer regions of our own Sun's protoplanetary disk. The gas production rate for 2I/Borisov varied smoothly with heliocentric distance, increasing as the comet approached the Sun and decreasing as it receded, following the expected behavior for sublimation driven primarily by solar heating. Superimposed on this smooth trend were rotational modulations and occasional outbursts, but the outbursts were relatively minor, factors of 2 or 3 brightness increases lasting a few hours, interpreted as enhanced activity from specific active regions rotating into favorable orientations rather than as irregular, unpredictable eruptions from chaotic subsurface processes. Dust production in 2I/Borisov also appeared typical, with a dust-to-gas mass ratio estimated near unity. Consistent with many solar system comets, the dust formed a symmetric coma and a well-defined tail pointing anti-sunward, both features developing smoothly without dramatic asymmetries or structural irregularities. Polarimetric observations indicated particle size distributions similar to solar system comets, with no obvious anomalies in composition or scattering properties. In nearly every measurable property, 2I/Borisov resembled solar system comets more than it differed from them. The most notable distinguishing feature was its trajectory, hyperbolic, clearly indicating extrasolar origin, but its physical and chemical properties suggested either that cometary formation processes are universal, producing similar outcomes in different stellar systems, or that 2I/Borisov formed around a star very similar to our Sun under conditions closely matching those in the outer solar system. 3I/Atlas, by contrast, defies easy comparison. Its carbon monoxide dominance exceeds even the most carbon monoxide-rich Oort cloud comets in our solar system. Its lack of clear rotational periodicity sets it apart from nearly all well-observed comets, whether of solar or interstellar origin. Its irregular jetting, with outbursts separated by unpredictable intervals and varying widely in intensity, suggests internal heterogeneity or structural complexity beyond what 2I/Borisov exhibited. One might ask whether these differences reflect formation in genuinely different environments: 2I/Borisov around a Sun-like star at moderate distances, 3I/Atlas around a colder star or at much greater distances where carbon monoxide dominates, or whether they reflect different evolutionary histories. Perhaps 2I/Borisov was ejected from its birth system relatively soon after formation, spending most of its existence in cold interstellar space with minimal structural modification. 3I/Atlas, conversely, might have experienced multiple stellar encounters or collisional events that fractured its interior, creating the heterogeneous structure that now produces irregular activity. Alternatively, the differences might be more prosaic, reflecting variations in size or composition within the normal range of cometary diversity. Even among solar system comets, diversity is substantial. Some show very regular behavior, others are erratic. Some are rich in carbon monoxide, others nearly devoid of it. 3I/Atlas might simply fall at one extreme of this distribution, while 2I/Borisov falls near the center, both representing valid outcomes of cometary formation, but in different regimes of parameter space. Statistical arguments, however, become difficult with a sample size of 2. The first 2 interstellar comets detected may not be representative of the interstellar population as a whole. Observational biases favor detection of brighter, more active comets, potentially skewing the sample toward objects with high gas production rates or unusual activity patterns that make them easier to spot against the background of faint asteroids and solar system comets. Quieter, less active interstellar comets could pass through the inner solar system unnoticed, never achieving brightness levels that trigger follow-up characterization. Furthermore, the detection circumstances differ between 2I/Borisov and 3I/Atlas. 2I/Borisov was discovered at a relatively large solar distance, allowing months of observations as it approached perihelion, passed closest to the Sun, and began its outward journey. This extended observing window permitted detailed studies of how activity evolved with heliocentric distance, how rotation influenced brightness, how composition varied over time. 3I/Atlas, discovered closer to perihelion during a period of high activity, offered a shorter baseline for observations before fading, potentially leading to different or less complete characterization. Despite these differences, both comets share the fundamental property of being interstellar. Both carry ice and dust from other stellar systems into ours. Both provide glimpses of planetary formation processes occurring around other stars. The fact that they differ so substantially in their observable properties suggests that the diversity of exocomets may be large, that planetary systems produce a wide range of cometary compositions and structures depending on local conditions, stellar properties, and evolutionary histories. Future detections of interstellar comets will add to this small sample, gradually building a statistical picture of what is typical and what is rare, what properties correlate and what vary independently. Until then, 2I/Borisov and 3I/Atlas stand as the only 2 well-characterized examples, each offering a different perspective on cometary physics and planetary system formation, each revealing that the processes shaping comets in other systems can produce outcomes both familiar and strange, both reminiscent of solar system objects and distinctly alien in their details. The comparison highlights 3I/Atlas's uniqueness, where 2I/Borisov reassured observers that comets elsewhere resemble comets here. 3I/Atlas challenges those assumptions, presenting a rhythm, or lack thereof, that refuses to conform to expectations, that demands explanations invoking structures or processes not commonly encountered in the well-studied population of solar system comets. It is the outlier, the anomaly, the reminder that diversity in nature exceeds the bounds of any small sample, that the universe contains variations beyond the familiar, waiting patiently in the dark to be revealed by chance encounters and observant telescopes. Models of porous ice and pressure attempt to capture the hidden architecture that drives the irregular jetting, to construct numerical simulations that reproduce the observed behavior by invoking plausible internal structures and physical processes. These models divide the nucleus into discrete computational cells, each assigned properties, ice composition, porosity, temperature, gas pressure, mechanical strength. Equations govern how heat flows between cells, how ice sublimates when temperature thresholds are crossed, how gas flows through the porous matrix, how pressure builds when gas production exceeds escape rate, how the crust ruptures when pressure exceeds strength. The starting point is the thermophysical model, which solves the heat diffusion equation to determine temperature as a function of depth and time. At the surface boundary, heat input comes from absorbed sunlight, calculated based on the sun's distance, the surface's orientation relative to the sun, and the surface albedo, the fraction of incident light reflected rather than absorbed. Heat loss occurs through infrared emission, following the Stefan-Boltzmann law, with emitted power proportional to the fourth power of temperature. The balance between these terms determines the surface temperature, which then serves as the boundary condition for heat conduction into the interior, beneath the surface. Temperature evolves according to thermal conductivity and specific heat capacity of the ice-dust mixture. These properties depend on porosity. Higher porosity means more void space, less material to conduct heat, lower effective thermal conductivity. Typical values for cometry material suggest thermal conductivities of perhaps 0.1 watts per meter per Kelvin, much lower than solid ice, about 2 watts per meter per Kelvin, but higher than vacuum. Heat diffuses inward slowly, taking hours to penetrate centimeters, as discussed previously, with the exact time scales set by the thermal diffusivity. When subsurface ice reaches its sublimation temperature, determined by local pressure through the Clausius-Clapeyron equation, it begins converting to gas. The sublimation rate depends on temperature, increasing exponentially with each degree of warming. The gas produced cannot remain in place. It must flow through the porous network toward regions of lower pressure, ultimately escaping to space if pathways exist. This flow is governed by gas dynamics in porous media, often modeled using Darcy's law or more sophisticated approaches that account for rarefied gas effects when pressures are low and pore sizes are small. As gas flows through the pores, it encounters resistance, friction against pore walls, collisions with other gas molecules, tortuosity of the flow path through the irregular network. This resistance causes pressure to build up in regions where gas production rate exceeds the rate at which gas can escape through the available pathways. Pressure gradients develop, driving flow toward the surface. But if the crust is thick or if pores are clogged with dust, the pressure can rise substantially before equilibrium is reached. The model tracks this pressure evolution in each cell. When pressure in a subsurface cell exceeds the mechanical strength of the overlying material, parameterized as a tensile strength threshold, typically set to values of tens to hundreds of pascals based on laboratory measurements of ice-dust mixtures, the crust ruptures. The model opens a new pathway to the surface, a vent through which gas can escape more freely. The sudden opening causes pressure to drop rapidly in the source region, and gas rushes outward, carrying entrained dust, creating a jet observable as increased brightness and gas production. The jet continues until pressure equalizes or until the ice feeding it depletes. Depending on model parameters, a jet might last minutes to hours. Once it stops, the vent may remain open, becoming a permanent pathway for future outgassing, or it may seal as dust settles back and clogs the channel. Different choices for these assumptions lead to different predicted behaviors. Models where vents seal produce discrete outbursts separated by quiescent periods, while models with persistent vents produce more continuous activity modulated by subsurface ice availability and heating patterns. To reproduce 3 ice/Atlas's irregular behavior, models must introduce heterogeneity, variations in ice composition, porosity, crust thickness, thermal conductivity across the nucleus. A homogeneous nucleus produces regular, predictable outgassing tied to rotation and solar heating. Irregularity requires that different regions respond differently to the same external forcing. This can be implemented by varying the model parameters spatially, creating domains where carbon monoxide ice is abundant and others where it is sparse, regions with thick insulating crusts, and regions where ice lies just beneath the surface. Some researchers employ stochastic approaches, randomly assigning parameter values to cells within specified ranges, then running many simulations to explore the range of possible behaviors. Ensembles of model runs show that certain parameter combinations produce irregular jetting resembling observations, no dominant periodicity. Varying outburst intensities, long quiescent intervals punctuated by brief activity. Other parameter combinations fail to match, producing either too much regularity or too little activity overall. The honeycomb interior suggested by some models envisions the subsurface as a network of chambers and channels created by previous sublimation events or by the comet's formation process. Large voids several centimeters across serve as reservoirs where gas can accumulate before finding a pathway out. Narrow channels connect these voids, acting as bottlenecks that restrict flow and allow pressure to build. Different chambers reach critical pressure at different times depending on their depth, their ice composition, their connection to the surface, leading to asynchronous outbursts rather than synchronized venting. Implementing such complex geometries in models requires either very high spatial resolution, which becomes computationally expensive, or simplified representations that capture the essential physics without resolving every pore and channel. Some models use dual porosity formulations, distinguishing between macroporosity, large voids, fast gas flow, and microporosity, small pores within the ice dust matrix. Slow diffusion, allowing both scales to be represented without prohibitive computational cost. Validating these models against observations poses challenges. The models produce predictions for surface temperature, gas production rate, brightness variations, jet timing, all quantities that can be compared with data. However, many different parameter combinations can produce similar observable outcomes, making the inverse problem non-unique. A model that fits the light curve might assume a particular distribution of ice and porosity, but other distributions might fit equally well. Without independent constraints on internal structure, from radar sounding or seismic measurements, neither available for 3I/Atlas, the models remain under-constrained. Nonetheless, they provide valuable insights. Even if the specific parameter values cannot be determined uniquely, the models identify which processes are necessary to explain the observations. The requirement for heterogeneity, for pressure-driven outbursts, for thermal lag effects. These emerge as robust conclusions even if the detailed implementation remains uncertain. The models also make testable predictions for future observations, how activity should evolve as heliocentric distance changes, how outburst frequency should correlate with solar flux, how the coma should respond to specific jetting events. For 3I/Atlas, the models suggest that the irregular rhythm arises from the interplay of complex internal geometry, compositional heterogeneity, and the time-dependent response of different subsurface regions to solar heating. The nucleus is not a simple object that can be described by a handful of parameters, rotation rate, ice fraction, surface area, but rather a complex system with internal structure that governs its behavior in ways not reducible to surface properties alone. The offbeat rhythm is the signature of this complexity, a pattern emergent from many small-scale processes occurring asynchronously within the hidden interior. The fading as distance grows marks the inevitable winding down of the comet's active phase, the gradual return to dormancy as solar heating weakens and subsurface ice cools below the temperatures required for significant sublimation. By late January and into February 2025, 3I/Atlas has passed perihelion and begun its outbound journey, moving beyond the orbit of Earth, approaching the distance of Mars, receding at velocities of tens of kilometers per second relative to the Sun as its hyperbolic trajectory carries it towards the outer solar system. Solar flux decreases with the square of heliocentric distance. At Earth's distance, approximately 1 astronomical unit from the Sun, the solar constant delivers about 1300 watts per square meter. At Mars's distance, roughly 1.5 astronomical units, this drops to about 600 watts per square meter. Beyond Mars, at 2 astronomical units, it falls to 325 watts per square meter. As the comet recedes, the sunlight striking its surface weakens steadily, reducing the energy available to heat the nucleus and drive sublimation. The surface temperature responds first, dropping over days as the reduced solar input no longer balances infrared emission at the higher temperatures maintained near perihelion. Subsurface temperatures follow more slowly, thermal inertia delaying the cooling just as it delayed the heating during the inbound approach. Regions several centimeters below the surface remain warm for weeks even as the surface itself cools, continuing to sublimate carbon monoxide as long as local temperature exceeds roughly 70 Kelvin. But the rate of sublimation declines exponentially with decreasing temperature. A drop of 10 Kelvin can reduce sublimation rate by an order of magnitude for carbon monoxide ice. As the subsurface cools from perhaps 120 Kelvin to 100 Kelvin, gas production drops precipitously. Jets that fired vigorously at perihelion, releasing hundreds of kilograms per second, weaken to tens of kilograms per second, then to kilograms per second, then to levels too faint to detect from Earth. The coma, sustained by ongoing gas emission, begins to dissipate. Previously ejected gas has already dispersed across millions of kilometers, its density dropping below the threshold where collisional excitation can produce detectable emission. New gas production slows, providing less material to scatter sunlight. The coma fades in brightness, shrinking in apparent size as the balance between fresh emission and dispersion shifts toward dispersion dominating. Photometric observations show the comet dimming by several magnitudes over the course of weeks. By mid-February, it has faded below naked eye visibility, requiring binoculars or small telescopes to observe. By early March, only larger amateur telescopes can detect it against the background sky. Professional observatories continue monitoring when possible, but the signal-to-noise ratio degrades as the comet fades, making detailed spectroscopy and high-cadence photometry increasingly difficult. The irregular jetting, so prominent during the bright phase, becomes harder to detect as activity weakens. Outbursts that would have caused noticeable brightness, increases near perihelion, now produce changes barely above the noise level in the photometry. The light curve, never cleanly periodic to begin with, loses even its quasi-periodic structure, settling into slow, smooth decline punctuated occasionally by small fluctuations that could be either real outbursts or statistical noise in the measurements. Spectroscopic observations, requiring longer exposure times to accumulate sufficient signal, reveal that carbon monoxide emission persists but weakens. The emission line intensities drop in proportion to gas production rate, which itself drops as the comet cools, by the time the comet reaches 2 astronomical units. Carbon monoxide production has declined by factors of 10 or more compared to perihelion values. Water production, already secondary to carbon monoxide during the bright phase, becomes even less detectable. Falling below the sensitivity limits of most instruments, the dust coma fades more slowly than the gas. Dust particles ejected near perihelion continue their outward expansion for weeks, still scattering sunlight even though no new dust is being produced. This creates a lag between the cessation of dust production and the disappearance of the dust coma, similar to how a fountain continues flowing briefly after the pump is turned off. Observers note that the comet's brightness declines more slowly than would be expected if only the ongoing gas production were considered. Evidence of this residual dust contribution, eventually. As February transitions to March and March to April, even the dust coma fades below detectability for most observers. The comet's apparent magnitude drops below 15th, then 16th, accessible only to large professional telescopes under ideal conditions. Observing campaigns wind down, data collection ceases, and the comet effectively disappears from the observational record even though it continues its physical journey outward. Beyond Mars's orbit, solar heating becomes insufficient to maintain significant activity. Carbon monoxide, the most volatile component driving the comet's jetting, requires temperatures above roughly 70 Kelvin to sublimate at rates significant enough to produce observable emission. At distances beyond 3 or 4 astronomical units, surface temperatures drop below this threshold for most or all of the nucleus. Subsurface temperatures may remain slightly higher due to thermal lag, allowing feeble outgassing to continue from the deepest heated layers. But the gas production rates fall to levels that produce no detectable coma. The comet enters a dormant state resembling its condition during the long interstellar journey: cold, dark, inert. The surface crust, now thickened by dust deposits left behind during the active phase, insulates the interior even more effectively than before perihelion passage. Any remaining volatile ice lies buried beneath this mantle, protected from direct solar heating, stable against sublimation until the next encounter with a star. If such an encounter ever occurs, the trajectory continues to carry 3 I/Atlas outward. It crosses the orbit of Jupiter roughly 6 months after perihelion, by which time it has long since faded beyond any practical detection limit. A year after perihelion, it passes beyond Saturn's orbit, 2 years beyond Uranus, 5 or 6 years to reach Neptune's distance, perhaps a decade or more to cross the Kuiper belt and enter the region where solar system comets originate. Throughout this outward journey, the comet remains dark and invisible, its presence known only through calculations of its orbit, through ephemerides predicting its position for observers who cannot actually see it. The fading is gradual but inexorable, a function of distance and physics rather than any property unique to this particular comet. All comets fade as they recede from the sun. All return to dormancy in the cold. For 3 I/Atlas, the fading also marks a transition back toward interstellar conditions, a return to the environment where it spent the vast majority of its existence. The bright, active weeks near perihelion represent an anomaly in the comet's history, a brief excitation triggered by passing too close to a star, an event that will not recur for millions of years if it recurs at all. Observers on Earth lose sight of the comet, their telescopes pointing elsewhere, their attention shifting to new targets, new transients, new phenomena requiring study. The data collected during 3 I/Atlas's visible phase, images, spectra, light curves, enters archives, awaiting analysis, comparison with future interstellar visitors, incorporation into models of cometary physics and galactic dynamics. The comet itself continues silently outward, carrying its offbeat rhythm back into the dark where rhythms do not matter, where there is no audience to observe, where time passes unmarked by jets or outbursts or any sign of activity. Only the slow drift through space toward destinations unknowable and unobserved. Trajectory, altered by invisible forces, becomes apparent in the astrometric data, precise measurements of the comet's position against background stars accumulated over weeks and months. Compared against predictions based purely on gravitational dynamics, if the sun's gravity and the perturbations from planets were the only forces acting on 3 I/Atlas, its trajectory would follow a precisely calculable hyperbola determined by its initial velocity and position. But comets experience non-gravitational forces from outgassing, and these forces, though small, accumulate over time to produce measurable deviations from the purely gravitational path. The mechanism is straightforward: when gas sublimates from the nucleus and streams into space. Conservation of momentum requires that the nucleus recoils in the opposite direction, the rocket effect. For a symmetric comet with uniform outgassing, this force would point directly away from the Sun, slightly altering the orbital energy and angular momentum, but in predictable ways. For an asymmetric comet like 3I/Atlas, with jets firing from localized active regions at irregular times, the non-gravitational force has components in multiple directions: radial, transverse, normal to the orbital plane, that vary with time as the nucleus rotates and as different jets activate. Measuring these forces requires comparing observed positions with predictions. Observers obtain astrometric measurements by imaging the comet against the background of distant stars whose positions are known precisely from catalogs based on missions like Gaia. The comet appears as a diffuse smudge due to its coma, but the center of light, the photocenter, can be determined to sub-arc-second precision in good conditions. These measurements, typically obtained several times per night over many nights, trace the comet's motion across the sky. Orbital dynamicists fit these positions using models that include both gravitational and non-gravitational accelerations. The gravitational part is well understood, computed by integrating the equations of motion under the influence of the Sun's gravity and planetary perturbations using numerical methods that account for the changing positions of planets as the comet moves through the solar system. The non-gravitational part is more challenging, typically parameterized using empirical formulas developed for solar system comets. The standard non-gravitational force model, developed by Marsden and colleagues decades ago, expresses the acceleration as a function of heliocentric distance with free parameters that capture the magnitude and orientation of the force. These parameters, often denoted A1, A2, A3 for the radial, transverse, and normal components, are adjusted through least squares fitting to minimize the residuals between observed and predicted positions. The resulting values quantify how strongly outgassing affects the trajectory. For 3I/Atlas, preliminary orbital solutions incorporating astrometric data through late January show evidence for non-gravitational accelerations. Though the uncertainties remain relatively large due to the limited observational arc and the comet's brightness variations complicating photocenter determination, the fitted parameters suggest a transverse component, perpendicular to the Sun-comet line and in the orbital plane, that tends to accelerate the comet slightly in its direction of motion, increasing orbital energy and making the hyperbolic trajectory slightly more open, increasing the velocity at infinity compared to the purely gravitational case. This transverse component is typical of cometary non-gravitational forces and arises from thermal lag. If jets fire from the afternoon side of the nucleus, regions that have rotated past local noon and are cooling but still warm enough to outgas, the reaction force has a component aligned with the comet's velocity vector, providing a net push forward. Conversely, jets from the morning side would decelerate the comet. The sign and magnitude of the observed transverse acceleration encode information about the average timing of jets relative to local solar time on the nucleus. The radial component, along the Sun-comet line, appears weaker in the fitted solutions, suggesting that jets do not preferentially fire either directly toward or away from the Sun. This would be consistent with jets originating from regions offset from the subsolar point due to rotation and thermal lag. As discussed previously, however, the uncertainties are large enough that a small radial component cannot be ruled out definitively. The normal component, perpendicular to the orbital plane, is the least constrained, because north-south displacements produce smaller changes in apparent position on the sky compared to east-west displacements for the comet's orbital geometry and viewing angles from Earth. Some orbital solutions include a small normal component, others set it to 0 within uncertainties. If present, it would indicate asymmetry in jetting between the northern and southern hemispheres of the nucleus, perhaps reflecting compositional differences or seasonal effects as different hemispheres receive different amounts of sunlight over the course of the comet's rotation and orbital motion. The magnitude of non-gravitational forces for 3Y/8less appears comparable to those measured for solar system comets of similar activity levels, accelerations of roughly 10 to 100 microns per second squared. Tiny compared to solar gravitational acceleration at 1 astronomical unit, about 6 millimeters per second squared, but accumulating over weeks to produce positional displacements of hundreds or thousands of kilometers, easily measurable astrometrically. These forces also affect the comet's future trajectory. The non-gravitational acceleration near perihelion changes the orbital energy slightly, altering the hyperbolic excess velocity, the speed the comet will have relative to the Sun once it escapes to interstellar space. Depending on the magnitude and direction of the force,